When you type a prompt into an AI assistant, the interface gives you the experience of talking to a person. It smoothly writes essays, analyzes data, and answers questions. But behind that clean text box is a chaotic blur of rapid-fire numerical code. Modern large language models are not monolithic, sentient brains. They are the highly engineered output of a strict three-stage industrial pipeline. At its core, the system is a stochastic, sequence-to-sequence token tumbler. It calculates the statistical probability of which text chunk should follow the last one, and it operates under severe computational bottlenecks. To reach the point where it can hold a conversation, a model must survive 3 evolutionary phases: pre-training, supervised fine-tuning, and reinforcement learning. The central engineering challenge of this entire process is forcing a system designed purely for statistical text prediction to somehow execute accurate, logical reasoning. Stripping away the illusion of magic and dissecting the mechanics of these 3 stages is the only way to master this tool and bypass its hard-coded limits. This vast expanse of server racks houses the physical infrastructure required for the first stage, pre-training. The objective here is to ingest massive swaths of the public internet to build a statistical simulator of how human text flows. But raw text cannot enter a neural network. It must be converted into numerical sequences through a process like byte pair encoding. The algorithm searches for common groupings of characters and assigns them unique integer IDs, breaking a single word like ubiquitous down into 3 discrete tokens. The model never sees the letters U, B, I, or Q. It only sees these numerical chunks. This is why language models routinely fail at simple character-level tasks, like counting the number of R's in strawberry. The letters simply do not exist in the model's field of vision. Processing these tokens requires staggering brute force. Engineers install thousands of high-performance GPUs to execute the trillions of matrix multiplications required to train the network to accurately predict the next token. The output of this months-long computational marathon is a base model. It is strictly a stochastic document simulator. A base model cannot assist you. If you ask it, "What is 2 plus 2?" it will not answer 4. It will statistically continue the format of the prompt, likely generating a list of similar math questions. Its hundreds of billions of parameters do not form a pristine database of facts. Instead, the base model acts as a lossy zip file. It contains a vague, compressed statistical recollection of the internet, ready for the next stage of development. To transform this chaotic document simulator into a helpful conversationalist, the model enters stage 2, supervised fine-tuning, or SFT. Engineers discard the raw internet data and replace it with hundreds of thousands of highly curated, human-written question-and-answer pairs. To teach the model how to hold a dialogue, developers inject special control tokens, invisible markers that define exactly when the human is speaking and when the assistant should reply. By continuously training on these ideal interactions, the model learns by imitation. It statistically adopts the persona, tone, and formatting of a confident human expert. But this imitation process introduces a fatal architectural flaw. Because the SFT dataset is filled with confident expert answers, the model learns to always sound confident, even when its lossy parameter network lacks the actual information. If you ask an older model to identify a completely fabricated historical figure, like Orson Kovatz, it will boldly declare him a 1950s author or a minor league baseball player. This hallucination is a mechanical failure. The model is statistically mimicking the format of a factual answer, using highly probable but entirely incorrect tokens. To mitigate this, developers systematically interrogate the model's knowledge boundaries during training. When it fails a factual check, they explicitly inject new SFT examples, where the correct target response is, "I don't know." The personality you interact with is not self-awareness. It is a trained statistical emulation of a human labeler's instructions, inherently prone to confidently bridging the gaps in its own lossy memory. Let's pause the training timeline to examine the inference mechanics. We need to look at exactly what happens under the hood when a user submits a prompt. This block diagram illustrates the core architectural constraint of the system. To generate a single output token, the data must drop vertically through roughly 100 layers of the neural network to calculate the next probability distribution. The amount of computation in this single vertical pass is strictly fixed. The network cannot loop back, stall for time, or allocate extra thought to a particularly difficult step. If you give the model a complex arithmetic problem and force it to output the final answer immediately, it will consistently fail. Demanding an immediate answer catastrophically compresses all the necessary logical deduction into a single, overburdened pass through the layers. The fixed compute budget is simply exhausted. The mechanical workaround is to force the model to show its work step by step, a technique known as chain of thought. Generating intermediate math steps horizontally distributes the computational load over time. Each newly generated token triggers a fresh, separate pass through the vertical layers. Every time a new token is created, it is appended to the context window, effectively serving as explicit working memory for the next forward pass. Large language models cannot think in the abstract. Their reasoning exists entirely as a distributed compute graph, spread horizontally across the generated token sequence. Returning to the training timeline, the model enters its third and final major stage, reinforcement learning. Supervised fine-tuning has strict limits. Blind imitation can teach a model the format of an answer, but it cannot teach the model to discover novel reasoning paths or fix internal logic errors on its own. To understand this progression, look at the structure of a standard textbook. It contains 3 distinct sections: exposition, worked solutions, and practice problems. Pre-training acts as reading the exposition to build background knowledge. Supervised fine-tuning acts as studying the worked solutions to learn the format of the answers. Reinforcement learning is the practice problems phase. The model is given a prompt and the final target answer, but it is deliberately denied the step-by-step solution. The model must generate multiple different reasoning pathways on its own. An objective function acts as an automated grader, evaluating which pathways successfully reach the correct final answer. Based on that grade, the network's internal weights are systematically updated. It physically rewards the specific computational pathways that efficiently navigate the logic puzzle. Reinforcement learning bridges the gap from blind imitation to actual problem solving, optimizing the network to navigate its own compute bottlenecks without relying on human examples. Understanding this 3-stage mechanical pipeline dictates how technical professionals should actually use the tool in daily practice. You must manage the system's 2 distinct memory types: the lossy, vague parameter network forged during pre-training, and the high-precision context window buffer utilized during inference. Look at this physical copy of Pride and Prejudice. Asking the model's parameter network to flawlessly recall and summarize its first chapter relies entirely on that lossy, compressed memory. It is an architectural error. To bypass parameter hallucination, you must lean on tool use, like web search or code interpreters. When encountering a gap in its knowledge, the model emits a special token that pauses inference entirely. This triggers a web search, retrieving the raw factual data and injecting it directly into the context window. Once this data is inside, it is perfectly available for the next forward pass. The model stops relying on vague memory and starts reading from the high-precision buffer. Large language models are not omniscient minds. They are stochastic reasoning engines. By mastering their lossy memory limits, managing their fixed compute budgets, and aggressively utilizing external tools, you stop being a passive prompter and become a master architect of the system.